Hi everyone, this is Srikanth, Assistant Professor of Triple Department. In this session, I'm going to discuss numerical problems on alternators. The equation used to calculate the induced EMF in an alternator. Let's derive the EMF equation of alternator below. Here, for the alternator, let us consider the P is the number of poles, phi is the flux per pole, N is rotor speed in RPM. As we know, the flux per pole is phi, therefore, each conductor is cut by the flux of phi p, and the time taken by a pole to complete one revolution is 60 by n seconds, because n is the revolutions per minute. So, the average EMF per conductor becomes flux cut by the conductors is phi p by time is equals to 60 by n, that is equals to phi np by 60, where alternator speed n is given as ns is equals to 120 f by p. That is, from this, f is equals to pn by 120 or n is equals to 120 f by p, where f is the frequency of the induced EMF. Here, F is frequency of the induced voltage which is generating in the alternator. Therefore, the average EMF per conductor becomes, here if we substitute this N value here, the average EMF per conductor is phi np by 60. In place of N, if we substitute 120 F by P, that is phi P by 60 into 120 F by P. Here 60, 120 will get cancelled, here will get 2F. Here the average EMF per conductor is 2F phi. Here PP also will get cancelled. And here let Z is the number of conductors per phase. Then the EMF pretty per phase becomes, here when we consider Z number of conductors are there, this is the average EMF per conductor is 2F into phi. If we consider there are Z number of conductors in each phase, then the EMF per phase is equals to 2F phi into Z, that is equals to 2F phi Z. Let T is equals to number of turns, that is 2 conductors per turn, and therefore Z is equals to 2T, and the equation becomes EMF per phase is equals to 2F phi Z, which is equals to, in place of Z we are replacing 2T, that is equals to 4F phi T. Assume the induced EMF is sinusoidal and its form factor is 1.11. So what is form factor is equals to, it is the ratio of RMS value to the average value, and where the RMS value is equals to form factor into average value. Here RMS value per phase is equals to 1.11 into 4F phi T, where VRMS per phase is equals to 4.44 F phi T volts. Now let's introduce a coin span of factor Kc and distribution factor Kd to get the actual induced EMF per phase. These are the factors which are corresponding to the construction of the winding factors. So based on the pitch value and distribution values, we are going to get the Kc and Kd values. That is Vrms per phase is equals to 4.44 into Kc Kd into F phi t, or we can also write it as 2.22 into Kc Kd F phi z pulse. Here V phase is the actual induced EMF per phase, Kc is coil span factor, Kd is distribution factor, F is frequency, and flux phi is flux per pole in Webers, and Z is number of conductors, and T is number of turns. If it is a star connected alternator, the line voltage will be equals to root 3 times the phase voltage. That is VL is equals to root 3 into V phase. If it is delta connected, VL is equals to V phase. Now, let us go with the problems. A 3-phase 50 Hz alternator is running at 600 RPM, has a 2-layer winding, 12 turns per coil, and 4 slots per pole per phase, and coil pitch of 10 slots. Let us find the induced EMF per phase if the flux per pole is 0.035 Webers. Here, the number of poles can be calculated as from the synchronous speed equation P is equals to 120 F by N. That is, from the Ns is equals to 120 F by P. From this, P is equals to 120 F by N. If we substitute these values, 120 into 50 by N is 600. That is, here number of poles is equals to 120 F by N, which is equals to 4 poles. Here the total number of slots is equals to number of slots are 4 and per phase 3, and each slot is going to have, each coil pitch is going to have 10 slots. That is equals to 4 3s are 12 into 10, that is 120. And the slot angle alpha is equals to 180 into 10 by 120, that is equals to 15 degrees. So KD is equals to sine 4 into 15 by 2 whole divided by 4 sine 15 by 2, which is equals to 0.958. That is the distribution factor. And the slat angle is 10 degree. Slot coil pitch of 10 slots, which is given. So the pole pitch is equals to 120 by 10, which is equal to 12 slots. Here beta is equals to 12 minus 10 into 15 degrees, which is equals to 30 degrees, where Kp is equals to cos beta by 2, that is equals to 0.966. The EMF equation of alternator is 4.44 phi f t into Kp Kd. Here 4.44 into 0.035 into 50 into 480 into 0.958, that is Kd, and 0.966, that is Kp, which is equals to ERMS is equals to 3451 volts. Here the next problem is a 3-phase 16-pole alternator has a star connected winding with 144 slots, and the 10 conductors per slot, which is given. The flux per pole is 0.02 Webers, which is sinusoidally distributed, and the speed is 375 rpm. Find the frequency of induced EMF. Phase EMF and line EMF. Assume the coil as full pitched. Full pitched is nothing but the Kp value is equals to 1 and number of poles is equals to 16 and slots is equals to 144. Z is equals to 10 conductors per slot and flux is given as phi is equals to 0.02 Webers and speed is equals to 375 rpm. Now, in order to find frequency, we need to calculate the frequency, induced EMF and the line EMF. So, for calculating frequency, we are using the synchronous speed equation. F is equals to Pn by 120. Here the number of poles are given as 16 into speed is 375 divided by 120, which gives us the frequency value as 50 Hz. Now we got the frequency value as 50 Hz. Now we are going to substitute this frequency value into the EMF equation of alternator, where the EMF equation of alternator is 4.44 into Kp Kd phi Ft volts. Now where Kd is equals to sine m beta by 2 by m sine beta by 2. Here the m value is nothing but number of slots per pole per phase. Here the number of slots are given as 144 per pole, that is number of poles are 16 divided by per phase is, there is a 3-phase machine, so which is equals to 3, where the n is number of slots per pole, that is 144 by 16, which is equals to 9. So beta is equals to 180 by n, which is equals to 180 by 9, which is equals to 20 degrees. Now this is the beta value. Now we need to calculate the Kd value, where Kd is equals to sine 3 into 20 by 2 divided by 3 sine 20 by 2, which is equals to sine 30 by 3 sine 10, which is equals to 0.96, where Z is equals to 10 conductors per slot per phase, that is equals to 10 into 144 by 3, which is equals to 480 conductors. Now Z is the 10 conductors per slot per phase. We are getting the 480 Z, that is number of conductors, and number of turns will be equals to divided by 2, Z divided by 2, that is equals to 480 divided by 2, which is equals to 240 turns. Now let us substitute all these values into the above equation. In this problem, the pitch factor which is given as the winding is full pitch winding which is given. So the pitch factor we have to consider as 1. So if E per phase is equals to 4.44 into 1 into 0.96 into 0.02 into 50, which is multiplied with 240, which is equals to 1022.97 volts. This is the E per phase, and where the line voltage is equals to root 3 into E per phase, which is equals to root 3 into 1022.97, which is equals to 1771.83 volts. Now the next problem is a 3-phase 1800 kVA and 3.3 kilovolts 50 Hz 250 RPM salient pole alternator has the following design data. Stator bore diameter is 230 centimeters and gross length of the stator bore is 38 centimeters. The number of stator slots is equals to 216 and number of conductors per slot is equals to 4. The sectional area of stator conductor is equals to 86 mm square. Using the above data, calculate flux per pole, flux density in the air gap. Here, the data corresponding to the constructional details are given along with the output parameters. We need to calculate the flux and flux density in the air gap. So first, let us go with the calculation of flux per pole. Here the flux per pole E phase is equals to 3300 by root 3, which is equals to 1905 volts. Here the number of slots per phase is equals to 216 by 3, which is equals to 72. The number of conductors per slot is equals to 4. So the total number of conductors per phase is equals to 72 into 4, which is equals to 288. These are the conductors. And now we need to calculate the number of turns, because from the EMF equation only we will get the flux value. So EMF equation we will get from the turns ratio. That is, number of turns per phase is equals to 288 by 2, which is equals to 144. And from the EMF equation, E phase is equals to 4.44 F5 number of turns per phase into kW. Here we are assuming it as kW as 0.955. If we substitute these values into the above equation, we will get the phi value is equals to E phase by 4.44 F into T phase into kW, that is winding factor, that is Kp into Kd. Here E phase is equals to 1905, which we got 1905. E per phase is equals to, we got it as 1905. 1905 by 4.44 into 50 into T phase is equals to 144 into kW is equals to 0.955, which is equals to 0.0624 Webers. And the flux density is equals to air gap flux per pole is equals to B average into pi dl by P. Here the diameter is 230 centimeters, length is 38 centimeters, Ns is equals to 250 RPM, and number of poles is equals to 24, where B average is equals to 5 by pi dl by P, which is equals to 0.0624 into 24 divided by pi into 2.3 into 0.38. We are writing in terms of meters. That is 38 centimeters will become meters. That is 0.38. 230 centimeters will become 2.3 meters, which will gives us the B average as 0.55 Tesla or Webers per meter square. Now the next one is, an alternator has no load voltage of 220 volts and a full load voltage of 200 volts. Calculate the voltage regulation of the alternator. Here the no load voltage and full load voltages are given. We need to calculate the voltage regulation of alternator. Here the voltage regulation of alternator is nothing but the voltage difference between the no load and full load. That is, when there is a load, there will be a reduction in the voltage because of voltage drops in the resistors, because the current will be increased. When the current increases, automatically the voltage drops also increases. So there will be some change in the voltage from no load to full load, and this change should be within the minimum values. Here the V no load value is 220 volts, V full load value is 200 volts. Substitute these values into the voltage regulation formula. Here voltage regulation is equals to V no load minus V full load by V no load into 100, which is equals to 220 minus 200 by 200 into 100. That is equals to 20 by 200 into 100, which is equals to 0.1 into 100. That is voltage regulation, which we are going to get it as 10%. So here there is a change in the change in the voltage from no load to full load is of 10%. Now an alternator has a no load voltage of 240 volts and a full load voltage of 210 volts. Calculate the voltage regulation of the alternator. Here the no load voltage and full load voltage values are given, and we have to substitute in the voltage regulation formula, where voltage regulation is equals to V no load minus V full load by V no load, which is equals to, we have to substitute these values. V no load value here is 240 volts, V full load value is 230 volts, 210 volts. Here voltage regulation is equals to 240 minus 210 by 210 into 100. That is equals to 30 by 210 into 100, which is equals to 0.1429 into 100%, where voltage regulation is equals to 14.29%. So the voltage regulation of alternator is approximately 14.29%. This is the alternator voltage regulation when there is from no load to full load, and that percentage is 14.29%. Now the terminal voltage of a three-phase star connected alternator is 10.5 kilovolts at a 0.8 lagging power factor when the alternator is fully loaded. After disconnecting the load, keeping the same speed and excitation, the voltage rise to 11 kilovolts. Calculate the voltage regulation. Here the terminal voltage is 10.5 kilovolts and the no load voltage is 11 kilovolts. The terminal voltage per phase of the alternator is V line by root 3, where terminal voltage per phase is equals to 10.5 by root 3, where V phase is equals to 6.06 kilovolts. And here the induced EMF or no load voltage per phase of the alternator is E naught line by root 3. that is 11 kV by root 3, which is equals to 6.35 kilovolts. And the voltage regulation of alternator is, voltage regulation is equals to no load voltage E0 minus V by V into 100. That is equals to E0 value is 6.35 minus 6.06 all divided by 6.06 into 100, where voltage regulation is equals to 4.78 percentage. So this is the way we have to calculate the voltage regulation for the alternators. In this session, we have discussed the voltage equation of alternator and some problems on alternator EMF equation and some problems on voltage regulation of an alternator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.